Welcome back. Today we are going to discuss various types of operation research models. Operation research is a highly sophisticated and systematic discipline. It revolves around the application of mathematical models and analytical methods to solve complex decision making problems. It's about taking a structured and quantitative approach to decision making. In other words, operation research is the science of making better choices. In the previous video, we had discussed definition, history, characteristics, and phases of operation research. Today, let's dive deeper in the different types of mathematical models used in operation research. These models are the essential tools that allow us to represent and solve complex problems. Operation research encompasses a variety of mathematical models, each tailored to address specific types of problems. Here are some of the key types: linear programming, integer programming, nonlinear programming, dynamic programming, simulation, queuing theory, decision analysis, game theory, network analysis. These various models offer versatility, allowing operation research to address a wide array of problems in different domains. They provide structured ways to find optimal solutions and make informed decisions regardless of the complexity of the problem. Linear programming. It's a powerful mathematical approach to optimize resource allocation where the relationships between the variables are linear. It's widely applied to situations involving the allocation of limited resources to achieve specific objectives efficiently. In linear programming, we have decision variables, objective function, constraints. Decision variables represents the quantities to be determined such as production levels or resource usage. Objective function defines the goal either to maximize profits or minimize costs. Constraints represents the limitation of resources or other factors. The primary goal of linear programming is to find the optimal values of the decision variables while satisfying all constraints. The solutions are typically represented as the points on a feasible region, and the optical solution is the point that maximizes or minimizes the objective function. Let's illustrate with a simplified example. Suppose a company wants to maximize its profit by producing two types of products, A and B, while considering constraints on the availability of the raw materials and labor. Linear programming can help determine the optimal production quantities for each product to maximize profit with these constraints. Integer programming. It is an extension of linear programming and it is used when decision variables must take integer values. While linear programming allows for fractional solutions, integer programming enforces that each variables are whole numbers. Integer programming is employed in scenarios where discrete decisions need to be made, such as selecting the number of units to produce, the number of vehicles to dispatch, or the number of items to stock. It is crucial when you are dealing with real world decisions that can be divided into fractions. Integer programming problems often have a mix of linear relationships and integer constraints. The objective is to find the optimal values of decision variables subject to these constraints. Let's consider an example. Imagine you are managing a manufacturing facility with limited production hours and you need to decide how many units of a product to produce. Since you can't produce a fraction of a unit, integer programming is used to determine the optimal whole number of units to manufacture. Nonlinear programming. It is employed when decision problems involve nonlinear relationships, making them more complex than linear scenarios. Nonlinear programming is essential in optimizing objectives with nonlinear constraints. This includes scenarios where cost functions, demand curves, or other relationships are not linear. Nonlinear programming can be applied in diverse fields such as finance for portfolio optimization, engineering for optimizing nonlinear processes, and even in machine learning for model parameter tuning. Let's consider a situation where a company wants to maximize its profit, but the cost function for production is not linear. Non-linear programming can help determine the optimal production levels in this non-linear context. Dynamic programming. It is a technique specifically designed to solve problems that evolve over time. Dynamic problem programming involves breaking down complex problems into a smaller subproblems and solving each subproblem only once. Dynamic programming is widely used in optimizing processes that occur over a sequence of decisions such as project scheduling, inventory management, and resource allocation over time. The beauty of dynamic programming is that it takes into an account the interdependence between decisions made at different points in time, providing efficient solutions. Imagine you are managing a construction project with multiple phases and you want to find the most efficient schedule while minimizing cost. Dynamic programming can help create an optimal project timeline. Simulation. It is another vital operation model, research model, offering a unique way to experiment with complex systems. Simulation involves creating a computer based model of a system and running experiments to observe its behavior under different conditions. It's especially useful when real world experimentation is impractical, expensive, or risky. Simulation provides a safe and a controlled environment for testing. Simulation finds application in various fields including healthcare, transportation, manufacturing, and logistics, allowing us to optimize processes and make data driven decisions. Suppose you are designing a new healthcare facility and you want to test different layouts to optimize a patient flow and resource utilization. Simulation can help you to experiment with various configurations without affecting real world operations. Queuing theory. It is all about the study of waiting lines and service times. Queuing theory focuses on understanding how waiting lines or queues form, how they behave, and how they can be optimized. This branch of operation research is crucial in scenarios where customers or tasks wait in line for services, such as in call centers, traffic management, and service facilities. Queuing theory helps improve efficiency, reduce wait times, and enhance resource allocation in systems with waiting lines. Consider a call center that wants to minimize the customer wait times and maximize service efficiency. Queuing theory can help design optimal call center operations. Decision analysis. It is our final stop in our journey through operation research models. It is a powerful approach for making informed decisions when faced with uncertainty. Decision analysis is a systematic approach to solving complex decision problems that involve uncertainty. It considers different decisions, alternatives, and their possible outcomes. It is crucial in fields where choices must be made under varying conditions and when the future is uncertain. Decision analysis helps identify the most optimal course of action. Imagine you are a financial manager considering investment strategies in a volatile market. Decision analysis can help you evaluate different investment options and their associated risks. Game theory. Game theory is a mathematical framework used to analyze and understand strategic interactions between rational decision makers. It is often applied to situations where the outcome of one participant decision depends on the decision of others, creating a game of strategic choices and responses. It is a valuable tool for studying conflicts, negotiation, competition, cooperation, and decision making in various scenarios. Imagine two companies engaged in a price competition. Game theory can help both companies analyze their pricing strategies and predict each other's responses to make informed decisions. Game theory finds application in wide range of fields including economics for analyzing market behavior, political science for studying voting strategies, biology for modeling evolutionary dynamics and many more. Network analysis. It's a method for examining complex systems and relationships through the lens of interconnected entities and their interactions. It involves modeling and analyzing networks to understand how information, resources, and entities flow within them. This can be applied to transportation systems, social networks, communication structures, and many more. Network analysis is essential for optimizing routes, identifying critical paths in a network, and improving overall efficiency. Consider a logistic company seeking to optimize its delivery routes. Network analysis can help identify the most efficient path to deliver goods and reduce transportation costs. Network analysis is widely used in the fields like transportation for route optimization, in social sciences for studying connection in social networks, in telecommunications for improving communication networks, and in project management for identifying critical paths in project schedules. By understanding these diverse operation models, we gain a deeper appreciation for how they can be applied to real world challenges. Thank you for your attention. See you in the next video to dive deeper in the world of operation research. Thank you for joining me today.